Good evening, welcome to this video for the 2020 Level 3 Aqueous Systems for Level 3 Chemistry. So we'll go straight into question 1. So an aqueous solution containing a mixture of ammonium chloride, NH4Cl, and ammonia, NH3, can act as a buffer solution. So they give us the Ka value of NH4+, plus, and they give us the pKa of NH4+, plus equals to 9.24. So question I asks, give the pH range over which the solution will function as a buffer. So the widely acceptable pH range for a buffer solution is within plus or minus 1 of the pKa. So according to the Henderson-Hasselbalch equation, so we have our pKa equals to pH plus log of the concentration of acid, I'll just call HA, over the concentration of the base, which is A minus. We see that if the pKa is within 1 plus or minus 1 of the pH, we know that the concentration of the acids or base, the difference will be by a factor of 10 on both sides, which is the maximum, okay? So we know that pH is within plus or minus 1 of pKa, plus or minus 1. So therefore, the pH range would be 9.24 minus 1, which is 8.24, and 9.24 plus 1, which is 10.24. So that would be our pH range for an effective buffer. Question II, explain why the addition of a small volume of nitric acid to this buffer solution will not result in a significant change in the pH. Alright, so a buffer solution contains both the acid and the conjugate base, and we know that nitric acid is a strong acid, meaning that it's going to fully dissociate in water to form our hydronium ions and our NO3 minus ions. So because we have both the acid and the conjugate base, we have both the NH4 plus and NH3. We know that the added acid is going to react with the NH3, and some of the excess acid is going to be reacted away. Because we know that the pH is a measure of the relative concentration of hydronium, and since the sum of the hydronium that is produced is going to be reacted with the NH3 to produce more NH4 plus, we know that it's not going to produce a significant change in the pH. So for this question, we can say that HNO3 is a strong acid. So it fully dissociates in water, so we can say it's going to produce some H3O plus ions in water. H hydronium ions in water. And we can say that the buffer solution will contain both the acid and its conjugate base. So we can say it has both the acid plus the conjugate base. I'll just abbreviate it to CB. So we have acid and the conjugate base. So that's our NH4 plus and NH3. And we know that some of the hydronium ions is going to react with that NH3. So we can say that some of the hydronium ions will react with the NH3, which removes some of the excess hydronium. And since we can say that pH is a measure of relative concentration of hydronium, so pH is measure of relative concentration of hydronium. Therefore, the pH is not going to change drastically. It's still going to change according to the Henderson-Hasselbalch equation. Once some of the NH3 reacts to become NH4 plus, the concentration of NH3 is going to decrease, and the concentration of NH4 plus is going to increase. So therefore, there is going to be some change in the pH, okay? But it's not going to be significant change. So therefore, there will be some change. Sorry, not some change. I should say minimal change. Therefore, minimal change to pH. Yeah, it's only going to decrease slightly when we add the excess hydronium, which is the HNO3. And in terms of our equations, we can say that one of our equations can just be the dissociation of nitric acid, so HNO3. If we add that to water, since HNO3 is a strong acid, it's going to give us hydronium and NO3 minus ions. And our second equation should involve the neutralization of NH3 and hydronium. So if we find some space here, I'll just write it up here, sorry. So we have NH3, and if we add that to hydronium, that's going to give us a neutralization reaction. We are going to get NH4 plus and H2O. So as you can see, some of the hydronium ions is going to be removed. Therefore, this will not result in a significant change in the pH. Question BI, we're going to calculate the mass of NH4Cl that must be added to 200 milliliters of 0.05 mole per liter NH3 to give a buffer solution with a pH of 8.75. So assume there's no change in the volume when the solid is added. So we know about the volume, so we just write down the volume. It's going to remain at 200 milliliters, and we should convert that to liters, which is 0.2 liters. And once again, we're going to be using the Henderson-Hasselbalch equation to figure out this problem. So we have our pKa is equal to pH plus our log of our acid, which in this case we have our NH4 plus over our NH3. And the brackets will just indicate that it's the concentration of the NH4 plus and concentration of NH3 in the solution. Right, so we can just substitute that our pKa is equal to, 9.24. So we can say 9.24 is equal to 8.75. Equals to 8.75 plus log, and log is base 10, so we should just write that down. Log base 10 of our acid over our base. So therefore, we can say that 10, so we can do minus 8.75 on both sides. We should get 0.49 on the left-hand side. And if we move the 10, if we simplify, we should get, we should have 10 to the power of 0.49. That is equal to the concentration of NH4 plus over that of NH3. We know the concentration of NH3 as of before the NH4Cl was added. That is 0.05 mole per liter. So we just have our NH4 plus, we don't know, over our NH3, which is 0.0500. So now we can multiply by 0.0500 on both sides. That is going to give us the NH4 concentration required is NH4 plus concentration required is 0.1545 mole per liter. And in order to find out the mass, we need the amount of NH4Cl that's required. Therefore, we need to look at the volume of NH3 originally, which is 200 milliliters. So we say that N is equal to CV, and that is equal to our required concentration, which is 0.1545, multiplied by the volume, which is 0.200. And that should give us an amount of 0.0309 moles. And if we use that, the mass of NH4Cl required will be equal to the molar mass multiplied by the total amount required, which is what we just figured out, which is 0.0309 moles. Our molar mass is 53.5, they tell us that, which is very handy. So that's 53.5 times 0.0309 moles, and that should give us an answer of 1.65 grams. So we should say that the mass required is 1.65 grams. And remember to round all your answers to 3SF. All right, looking at question II. Explain whether the buffer in part I will be more effective at neutralizing strong acid or strong base. For these types of questions, like the most effective buffer is obviously when the amount of acid is equal, the concentration of the acid is equal to the concentration of the base, because it has an equal ability to neutralize either the added acid or the acid base, since there's equal amounts of the conjugate acid and the base in order to react with both the added acid and base. So in this question, we need to look at the pH of our buffer solution, which is 8.75, as well as the pKa, which is 9.24. So in this case, we see that the pH is actually less than the pKa value. So we have, so we just write it down. So we say that pH is less than pKa. So if we write out our Henderson-Hasselbalch equation, so I have trouble pronouncing it sometimes. So we have In this case, we'll have 10 to the power of 0.49. That is 3.09 is equal to the acid, which is NH4 plus, over the base, which is NH3. Alright, so in this case, we see that there's actually 3.09 times more NH4 plus in the solution compared to the NH3. So therefore, since there's more acid in the buffer solution, then it's going to be more effective at neutralizing the base, because as more base is added, there's more available NH4 plus to react with that base. Therefore, we say that this buffer is more effective at neutralizing the base. Since there's less base NH3 currently in the buffer solution, there's less available NH3 to neutralize the strong acid that's going to be added. Therefore, we say that this buffer solution is less effective at neutralizing strong acid. So we can just simply just say, so for any situation, if the pH is lower than the pKa, there is more acid than the base in terms of the buffer solution, and it's going to be more effective at neutralizing the strong base. If it's the other way around, if we have pKa greater than pH is greater than pKa. In this case, we're going to have more base than the acid. Therefore, this particular buffer solution will be more effective at neutralizing strong acid because it's more base. But in this particular case, it's the pKa is greater than the pH. So we say that therefore from our equation we can see that there is 3.09 times more NH4 plus than NH3 in solution. So we can say, therefore, the solution is more effective at neutralizing the added base, since there's more acid available to get rid of the added OH minus. Since there is more NH4 plus available to react with the added. There's more available NH4 plus to react with the added base. Obviously, this is for small volumes of added strong base, for small volumes. Alright, so that's all we need for that question. And looking at question CI now. So solutions of equal concentration were prepared for each of the following. We're looking at HBr, CH3NH2, and NH4Cl. So rank the solutions in order of decreasing pH in the box below. So which of these species would have the highest pH? In this case, it would be the weak base, which is CH3NH2. It is an amine, which is slightly basic. It is a weak base. So the weak base is going to accept a proton from water, and some excess OH minus will be produced. There's going to be more OH minus than hydronium in the solution. Therefore, the pH is greater than 7. If we look at the other two solutions, we have HBr and NH4Cl. We know that NH4Cl will fully dissociate in water to form our NH4 plus ions and Cl minus ions. And we know that NH4 is a slightly acidic, is a weak acid, so therefore it's going to donate a proton to water, and it's going to form NH3 as well as some excess hydronium ions. But since it's weak, it's not going to go to completion, so only a small fraction of the NH4 plus ions will dissociate to form NH3. So the solution that contains NH4Cl will be slightly acidic. If we look at HBr is a strong acid, meaning in this case, its pKa is going to be very high, since pKa is actually just a measure of the extent of dissociation for a particular acid. So the pKa for HBr is going to be very high. So therefore, we're going to just assume that it's going to be fully dissociation. So all of the HBr particles will dissociate to form hydronium and Br minus. Since there's a lot more hydronium ions than OH minus ions, the pH for HBr is going to be very, very low, and it's going to be lower than that created by NH4Cl. So we should have our order pretty easily established here. So we're going to have our weak base, which is CH3, going to have the highest pH. Sorry. That's going to have the highest pH, followed by NH4Cl, followed by HBr. Alright, so justify the order. Okay, so I guess we could start with the lowest pH, which is HBr. We can say that HBr is a strong acid. It's a strong acid, so pKa is very high, so pKa large. So we can say that we can assume that all of the HBr particles will be dissociating to form we should say dissociate. We'll dissociate to form H3O plus and Br minus. So we can say that there is a high concentration of hydronium. And therefore there is a low pH. Oh, sorry guys. I don't have my pen currently with me right now, so I'll have it by next week. But I currently don't have my pen, so that's why the writing might be a bit tricky for me right now. I apologize for that. But okay, so back to the question. Because there's a high concentration of hydronium ions, so therefore the pH is going to be low. The pH is low. Okay, so we can say in terms of the equation, we can just write the full dissociation of HBr in water. So that's our equation, since it's a full dissociation, because HBr is a strong acid. And for our second one, we can say it's NH4Cl. So NH4Cl is fully dissociates in water. Fully dissociates in water. And that's to form NH4 plus and Cl minus ions. So it's going to form our NH4 plus and our Cl minus ions. And we're going to say that NH4 plus is a weak acid. So we can say NH4 plus is a weak acid. So therefore, some of the NH4 plus will further react with water as an acid to donate a proton to water. And this obviously is going to form, this forms some excess, hydronium. But you can say that since NH4 plus is only a weak acid, the amount of hydronium formed is not as much as the HBr for the same concentration of HBr. So some excess hydronium, we can say, since NH4 plus is a weak acid, so we can say that pKa of NH4 plus is far less. Oh no, sorry, just Ka of NH4 plus is far less than that of HBr. But we can say that we need more space, don't we? Oh, we need more space. Okay, so let me just rub out what we wrote on top here. So So Ka of NH4 plus is far less than that of HBr. So therefore, the solution created with NH4 plus is less acidic. NH4 less acidic, okay? So that finishes our discussion. Oh, we still need to write the equation, sorry. For the equation, it's pretty simple. We can just say our first dissociation, we have NH4Cl. That's just going to go dissociate in water to form NH4 plus and Cl minus ions. And we have NH4 plus is going to further react with water. So some of the NH4 plus is going to donate a proton to water. So this is an equilibrium reaction, and that's going to form NH3 and some excess hydronium ions. Right, so those will be the equations for the NH4 plus. And if we look at the weak base, let me just start again, write everything out here. All right, so finally we're going to look at our base, which is CH3NH2. We're going to say that CH3NH2 is a weak base. It's a weak base, so therefore some some of it will react with water. To accept the proton, so it's going to accept a proton to form excess OH minus ions. Oh, sorry, not to accept, to create excess OH. So for this solution, we can say that the OH minus concentration is going to be greater than that of hydronium. Hence, this is a basic solution that will have the highest pH. So therefore, this has the highest pH. Alright, so in terms of the equation, we can just write the reaction of water, the partial reaction of water. Alright, so that'll be the equation for the base. And I believe that's all we really need to talk about for this question. Okay. Alright, so looking at question II, if the NH4Cl solution is a pH of 4.7, calculate its concentration. So what I like to do for these calculate concentration questions, I like to write out the equation first. So I'll have our NH4 plus. That's going to react with our water partially to create some NH3 and some hydronium ions. And if we write our equation for our Ka, so we can say Ka is equal to our NH3 and our hydronium all over the concentration of NH4 plus. So a pH of 4.7, that indicates that we know about the hydronium ion concentration is, we can use hydronium ion concentration equals to 10 to the power of negative pH, which is 10 to the power of negative 4.7. That is equal to 1.995 times 10 to the power of negative 5 mole per liter. Alright, and we know for the dissociation of NH4 plus, we know that equal amounts of NH3 and hydronium will be formed. And since we're initially only adding NH4Cl, there's initially no NH3 in the solution. So any NH3 that is produced will be created through the reaction of NH4 plus with water. So therefore, equal amounts of excess hydronium and NH3 will be produced. And the amount of hydronium produced by the auto dissociation of water is not very significant in this case because our hydronium ion concentration is much greater than that created by dissociation from water. So we can safely disregard the dissociation of water. And we can say that the only hydronium and the only NH3 that's created is only from this reaction of NH4 plus of water. So therefore we can say hydronium concentration is equal to that of NH3. Sorry if I can write it properly. Sorry. Well, it's equal to NH3. And we can simply use this information to calculate our Ka. Not Ka, our NH4 plus, since we know what our Ka value is. I believe it tells us somewhere. Yeah, pKa of NH4 plus is 9.24. Okay. So pKa is 9.24. So therefore our Ka is simply 10 to the power of negative 9.24. So we can say that 10 to the power of 10 to the power of negative 9.24 is equal to 1.995 times 10 to the power of negative 5 squared divided by concentration of NH4 plus. So technically, if we were to do this very precisely, we would say that there's originally some concentration of NH4 plus, and this much of NH4 plus concentration would have reacted away to form NH3 and hydronium plus. So the technical way to write it would be some X concentration of NH4 plus minus the amount of hydronium and NH3 created, which is our number above. So we write an equation showing this. But since we can say that the Ka of NH4 plus is super small, therefore this value is very small compared to this value. Therefore we can say it's not very significant, so we can just say it's just all over X. But if you were dealing with some some acids with bigger pKa, you can't really ignore that anymore because the amount reacted and the initial amount is much closer. But in this case, since the Ka is so tiny, then we can just assume that it's just over some X. Okay. I just thought I'd let you know about that. Anyway, so if we solve for X, we should get, I believe it's the concentration of NH4 plus equals to 0.6918. And if we want to round that to 3SF, we should. And that equals to 0.692. And that's our final answer for this question. Okay, we rounded to 3SF. So our concentration of initial concentration of NH4 plus would be 0.692 mole per liter. And that's it for question 1. Okay, so I'll leave question 2 for another time, maybe for when I find my pen, because I found out that it's very bothersome to write with my hand. So next video, I'll try to get it out as soon as possible, but that's going to be when I get my pen, so it'll be easier. It'll be much faster and much easier for me to write. But until then, I hope you really enjoyed watching this video, and I hope to see you all in the next one. Thank you. Bye.